What do you mean wants to join? Wants to come. Okay. Wait. Okay. So how we solve it? The first, we solve as a optimal solution. Then as we are looking at the optimal solution, we see some portion and some portion repeating. Then we can rewrite, we can write into the repeating problem, which means it is adaptable for the dynamic programming. The basic concept of dynamic programming is using the previously computed result. Okay, then we practice with the LIS with the 2 pointers, I and J, and we solve with the maintain an active list, which is n log n space, and fast enough, and it's very intuitive. I think you know how to solve this. Won't be an issue. Then today I want to talk about the LCS, the longest common subsequence. Longest common, the LCS is, let's say you are given 2 sequences, string 1 and string 2. Find the length of the longest subsequence present in both of them. Say I have string 1 and string 2. What is the longest subsequence? Longest common subsequence. A is existing, okay, fine. B, okay. C does not exist any. D, okay, D looks fine because D is here, and FG. So longest common subsequence is A, B, D, F, G. Okay, that's the concept of longest common subsequence. Where is being used? Where is being used? Longest common sequence. Where is very applicable? I believe you are using this every day. You are using this. You are so in a search engine. You are using
Control
this LCS every day. Any idea? What does that? What, Kwangmin?
Control F.
Control F.
When we look for some words or not.
Okay. Okay, good approach. Someone else? Where we use this? LCS. Control F in the PDF version. In the PDF, you're looking for some word, but you don't know exact then. But I believe PDF, you need to know exact the even in the shortest, it should be exact. Then you can find it, right? But let's say you want to looking for say you want to looking for in the Bible. Let's say there's a Kwangmin. Let's say Kwangmin's name is in the Bible. By looking at KAMN, you're never going to find the Kwangmin in there, right? So it has to be matched somehow. Then you may find it, right? Then I'm telling you, we are using this LCS every day. Where do we using this?
Maybe suggestion box on the what is it, text field.
Oh, okay. All right. Good point. Anyone else?
Autocorrection.
Autocorrection. Yes, suggestion box and autocorrection. So you type it in a like an Apple phone. People are suggesting a weird pattern, right? Also, while you are typing on the Google, you type something, but it doesn't need to be exact word. But a similar, the dictionary level word is appearing. We call, do you mean this? Do you mean this? Right? Then how can Google can find that so quickly? So that's what we're going to talk about today. So that's using the LCS, also edit distance. Okay, we're going to talk about 2 topics today. So I'm telling you, today's LCS is that important. So LCS with the 2 string L1 and L2. there are two cases: the last character matches or no matches. Okay. And if it is match, oh, I found the match. If not, okay, I may looking for the other sequences by subtracting one. Subtracting one. What do you mean? So let's say you are looking at the last point. Okay, you match. Then what do? Your pointer moves to this point, pointer moves to this point. If not match, what do? I'm repeating by moving one point and keep repeating on this. Or I'm decrement this one pointer, then keep repeating on this. Do you see what I do? If not, please ask questions. So well, I think I have a practice on the next slide. So go to one, decrement. By decrementing one, I'm looking for the matches. Okay. So if the character do not match, I'm finding the maximum match that I can find with the subtracted result. Let's practice with this. So I have L1 and L2, string 1 and string 2. String 1 is AGG TAB. String 2 is GXT XAYB. What is LCS of these two? How can I find it so quickly or efficiently? So first thing, my approach is from the back. If it is match, okay, then what do? I'm looking for the second match. Oh, A and A. Oh, second match. Oh, second match. Then what do? Decrement it and keep looking for in here. Oh, T and T. Okay. Then decrement in here, decrement in here, A, G, 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 X. So G is match. That's what we can do. That's what human can do, right? So can you make this approaches is work smoothly and efficiently on the computer? How can you make this? This is how human brain work, right? Then how can you make your computer can do this in a fast way? This is what I just used in the previous lectures. If it is match, the last element match, then increment 1 and keep repeating LCS with a decrement size of both. If not, I'm looking for decrement 1, then keep looking for LCS, right? So if I'm looking for the simpler example, AXYT, AYXT, if it is match, not an issue. But if it is didn't match, what do? Increment this pointer, then AXY and this one, then repeating LCS on this size. Decrement this size and compare this. So AXYT and AYG. Then if it doesn't match, I'm keep repeating the same procedures. Meaning I can keep using my previously computed result, okay? Which is exact pattern for dynamic programming. So let's try to solve this from. Do you know why I cannot delete the, because I don't pay it? So I need to be subscribed on 365. I don't want to. Then I can do this. Okay, let's solve this. So I just show you the very basic optimal solution, and maybe we can think about the faster solution to find the LCS. How can you find this? So let's think about for 2 minutes. Then I'm going to ask you to find a creative idea. So for today, I'm going to ask you Jungmin, Roshan, and Yejin, and Oh Young, and Ko So-young, and Kang Seung-jae. All right, let's think about for 2 minutes, then we can share your thought. Ready? 고소영, you wanna try?
Sorry, I can't get the answer.
Any approach is fine, don't worry. Okay, anyone else? 정민?
So you mean like how to find the longest common subsequences?
Yeah, that's the way.
I'm not sure, but I think we can approach it like recursively.
Mm.
So when two of the what is it, like letter, if they are both of them are zero, both of them lengths will be with lengths are zero, and then like return zero. But when if assume that L1 is length of L1 is 6 and length of L2 is 7. So we can find out that they are both of not 0. So and then find out that if the last, can I annotate? So everyone's assume that length of L1 is A and length of 2 is B. So A minus 1 and so compare this one, and then if it is same, and then keep one, and then compare the next one. But if they are not like same, and then compare another, like this one and this one. I don't know how to write, but
Okay. So I think you are trying to explain what we did in here, right? Isn't it?
it's
Okay. Anyone else? Thank you, Jungmin. Anyone else? No, nobody?
Professor, may I try?
Sure.
I think we can define a matrix that tracks each element. I mean, and we have two indexes for each of the array of two strings. Starting from the last sequence, if last position, if the two elements is equal, then we add 1 and then move the pointer to the left. I mean, for the both arrays. And then save the value to the so add 1 to the previous diagonal value. And if the value at the last position is not equal, then the compute the max of the value of the matrix value that it's really hard to explain, but I minus 1 comma j and I comma j minus 1.
Okay.
So left side and the upper
So,
side.
Yeah, L1 minus 1, then L2 for the
Yes.
max. And you do L1 minus 1, L2, then you do LCS, then LCS of L and L2 minus 1. Is it what you're saying? Then max of it. Right.
Yes, that's right.
Then
And then after the iteration, then return the value of the last element of the matrix. So we have an index I and j, and we can return. So I mean the value of the ij. I mean the yeah.
okay. So you are returning the length of it, length position index, right?
Yes, right.
Okay. All right. Thank you. So I may take over from here. So both of you, thank you for your voice. And basically, you guys doing the recursive way, right? Say, let's do in dynamic program way, in a DP way. In a DP way, we have the tabularization and the memoization. Using my previous one is memoization, right? So LCS, I make the 2 columns in 2D matrix. So longest common sequence of the 0 to 0 is there's nothing common. Nothing to A is nothing common. There's no common, right? How about G and this guy? Oh, nothing common. G and A, nothing common. GAG, okay, it is common. Then G and G again. So I have result 1, right? By matching in G and G. GG and G is the same as previous one. And G and GGT is the same as previous one. G and GGTA is same as previous one. G and GGTAB is the same as previous one. Do you see how I done? So my input, and I'm moving my pointers one by one. Moving my indexes one by one. I'm looking for how close are they. Okay. So let's look at the X, meaning G and X. Okay. So X is nothing to do so far. Okay. At this point, which value should I choose? I should choose 1. Why? Because my input is not just X, my input is a GX, and I have a G, which means I can take this one or this one. So max of these, okay? Whoever, which is a bigger number, if it doesn't match, I'm choosing the bigger number. If these two, it doesn't match, X and T, it doesn't match, A doesn't match, so either of 2, I'm choosing the bigger number. Either of 2, I'm choosing the bigger number. Okay. All right. So T, GXT, and 0, meaning either of 2 doesn't match. I'm choosing the bigger number. Okay. So T and G doesn't match. So either of 2, I'm choosing the bigger number. GT, no match. Either of 2. Oh, T and T. Okay, it match, meaning bigger number plus 1. Okay. T and A, no match, so bigger number. T and B is just bigger number. Do you see how I done? Okay. X is not matching in here, so what do I do? Either of 2, bigger number, 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 either of 2, bigger number. Okay, let's A. Oh, A is matching, right? So either of 2, bigger number plus 1. G and A is doesn't match, so bigger number. G and A is doesn't match, bigger number. T and A doesn't match, bigger number. Oh, A and A again, either of 2, bigger number plus 1. Okay, B and A don't match. Clear? Then Y is not appearing in here, meaning I can choose the bigger number, which is just copy of the previous one. Then B, either of 2, bigger number, either of 2, bigger number, either of 2, bigger number, either of 2, a bigger number, either of 2, bigger number. Okay, now I match either of 2, bigger number plus 1. Okay, so input L1 and input L2, LCS is 4. Oh, I just found the answer. So since I just did the matrix computation, it could be much easier. I can make this in a 2-dimension array, but I can do this also length of 2 dimension. Clear? I don't need to maintain whole, but I only need to maintain my previous one and my one, my previous one and my one. So I can compute these, then move recursively, go to this point, and either of 2 and bigger number, either of 2 bigger number. Then I can keep swapping. Then I can ignore the one of the row. Then I can keep which means I can only need to have 2 times of one of the length of L1 or L2. Okay, the longest one, let's say longest one of the L1 and L2, 2 times of it. That's it. Clear? Do you see how I done it? Using the DP, and I'm using the concept of it. If it is match, I'm increment +1 of the previous result of max. If not, I'm just using the max of these two. Okay, so this is the result. Okay, code that I'm using is in here. So I define the 2-dimensional array. Then from there, if it is match, my value is +1. If it's not match, either of 2. Okay. So if it is match, I'm adding the diagonal value. Okay, let me try to solve again. So the code says, if it is match, diagonal value +1. If not, max of vertical or horizontal. Okay, let's try to solve it again. So don't match the max of 2. Oh, it does match diagonal +1. It does match diagonal +1. Doesn't match max of it. Doesn't match max of it. Doesn't match max of it. X is not matching. So either of 1, max 1. Okay, T does match. T does match, therefore bigger 1. Bigger 1. Oh, it match, therefore 2. Bigger 1 and bigger 1. And doesn't match. X is doesn't match. A, oh, match, diagonal +1. Doesn't match, bigger 1. Doesn't match, bigger 1. TT doesn't match, bigger 1. Oh, it's match, diagonal +1. Doesn't match. Y is not appearing, so I can. Okay, B doesn't match, bigger 1, bigger 1, bigger 1, bigger 1, bigger 1. If it's match, diagonal +1. Okay, the same result. So the code says, if it is match, I'm adding diagonal +1. Diagonal meaning I have to reduce both sides. Okay, if not, I'm using this. So the basic concept of the code is the same. Either I solve it in the recursive way, or I can solve in the memorization by using the memory, the matrix. Okay, all right. Any question about the LCS? No? Okay, let's move on to more fun, which is edit distance. So,
Professor, I want to ask you about a previous question. Is it what's the time complexity of second one?
the second one's time complexity. Okay. So let's look at the space that I use. Space, what did I use? I only used the 2 times of length, 2 times of max of length of L1 and length of L2, right? Why do I say 2 times? I don't need to maintain full array, but I only use 1 time previous. Therefore, if I maintain 2 dimension, 1 dimension with the size of 2 row, then I can solve it. Okay, that is precise space complexity. Time complexity. What's the time complexity of this one? If the input is there, the input is size of n. Let's make n and n. So I'm keep if I initiate everybody as a 0, okay, then I only need to compute. And so for m, 1 to m underscore is 1 to m, then for n equal 1 to n underscore 1 to n. Therefore, complexity is n squared. But in the view of the complexity, I can make it much simpler with the matrix computation. Okay, so size of it is this m and n is not multiplying each other. Therefore, in reality, in the equation, it looked like n squared, but in reality, it looked like constant. How that is possible? Because I'm keep maintaining the matrix. Let's say it is 2-dimensional matrix. I'm keep computing the computing point that I'm using, this previous one, and compare 3 points and choose that point. Compare 3 points and choose that point. So if I'm asking you, what's the worst case computation, then it should be big O n squared. But in reality, in the view of the computer programming, it works like constant. That's the we call the power of the dynamic programming. Clear? Any question about the LCS? Okay, can I move on? No question. All right, so back to the point. Yeah, edit distance. So edit distance, we are using edit distance every day, like we talked about. Okay, let's talk about this. So when you type something, GRAFFE, in the Google search, what does they ask? What does the Google search pattern suggesting for you? Either of some, right? Either. So let me actually type this. So Google. And they are asking giraffe or griffin and giraffe tongue and graphics time. Then how this all working? I even typed the wrong, right? Then they are automatically suggesting these number of set, right? That is edit distance. That is based on the edit distance. Okay, point. So what is the closest one on this? How the computer understand if I type in the wrong way? So because I'm human, I make mistake, right? Then computer should suggest the easiest way or better way to do. So they may suggest these guys, and maybe this looks closer. Then how can we quantify? Then how can you score them? Then what letters should I suggest first? Okay. Then we called how similar are they? How similar of the two strings? Let's give another example. Computational biology. So let's say this is your nucleotides, two sequences of nucleotides. How similar are they? What's the score of similarity? Let's say you just found the crime scene and you just sampled some DNA of it, and you want to run a match of the criminal record. Then you found the L1 and L2. L1 is our sample, and L2 is so many, and they are the book of it. So DB of criminal. So you have to run through L1 and L2. Then you'll find the closest pattern. Okay. In a DNA world, there is no perfect match. And we can always say, oh, it's a 95%. 95.9%. We don't say 100%. There is no 100% because of the sequence of DNA. Okay, and how can you make this quantified number? Say I have L1 and L2, then how can you compare up these two? Let's think about this. How? So maybe a little advanced version of the LCS. How can we quantify the score? Let's think about for 2 minutes, then we can discuss together. Ready? Who want to try?
Professor,
Yeah.
in this scenario, the one that matters is a sequence, not like how many C's are. The sequels are the sequence is important.
So how many matches are important? The important thing is how many common matches.
Matches of.
C is a C and T the T. So
Okay.
maybe it is a little expanded version of the LCS. How can you do this?
Can I try?
Sure.
So compared to LCS, I think we can look at the chunks instead of just one letter. So I see A, like from L1, I see LAG, and L2, the second from the left, I see AG as well. And for the from L1, I see CTATCAC. And for L2 as well, CTATCAC. So like keep going for this for the entire string, and we can try to match if they work out well.
So how do you program it?
That's a very good question.
Okay, thank you, Wang Min. Anyone else? So this is the resulting alignment, meaning if we can align two input properly, I can find the match more precisely. Like Kwang Min says, okay, AG appearing here, CTATCAC appearing here. Okay, something is not matching. Up here, C is matching. So I can match in here, meaning I can quantize. Okay, if I do delete this, replace to G, and delete this, and replace to T, and add to 2T, and adding 3 letters, then it could be 100%. But because of this point, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of it's 13, including the first one. 13 out of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5, 5, 5, 5, 5, and 2. 10, 20, 30, 7. So I can quantize. It's about 65% accuracy. So out of 32, 24 is matching. So you have a probability of the 65% to be a criminal. That is how it works. That is how it works. Okay, in the DNA matching. So where's this similarity is working? So machine translation, information extraction, and speech recognition. We're gonna talk about this now. So let me share the one video with you. So this is example of the Google I/O. So what can you see? So what makes your computer is a similar to human? Okay, I can translate it. So whenever I write something, if the computer writes something and if I write something, there are differences, right? Even let's say you are English native, but if you read the untrained person's writing, whose native is not English, then you can see, oh, I don't know, I don't exactly tell you, but that's an unnatural thing. Unnatural point is there. Same thing. If the computer is well trained, there's still the numbers, the points that make so distinctive to the human. Okay, so Google's job and Google's goal is make the AI as close to human, then human cannot recognize the difference. Okay, so go back to the slide. So if I translate something, then how close is the human saying? Right. Let's solve this problem. So application of edit distance in natural language processing. Who can read this? Anyone? Nobody? Right? I choose the, Can you? No. Do you learn it? I don't think so. Right? So this means spokesman confirms senior government advisor was shot. Okay? The Arabian language. Then if the human translated, spokesman said the senior advisor was shot dead. Machine did good job, but it's not perfect as human did. It's not natural. Okay, in terms of the in the view of the grammar, it's not an issue. But in the view of what the letters, the sequence of the languages we are using, we don't use that way. We are using somehow, but the human translation is much more natural. Okay, then let's say you translate it just word to word, word to word, word to word. It does make sense, right? From that level, then how can you make more natural? Right. So let's say you are the main core software engineer in NLP in the Google. What you're gonna do from text to text translation, and you have collection of the text. Then you want to change somehow. You want to change some. Then you want to look like more natural. Then how can you do? Say you just hired who can speak in Arabian and English, and they translate in that way. Let's say it is L1 and L2. Then by doing some actions, something like I can replace conform to said, or by adding a the, or by removing government, and by adding a that, then it is more natural. Then you can keep learning, then make a quantify. Then next time when there's a new text, I may have some translate languages, but if man translate language or not, then I do the same procedure, same modeling that I did in the human data, then I can translate much more naturally. Okay, so how to quantify is edit distance. Do you see the point? Okay, we're going to talk about this. So edit distance is given two strings, string 1 and 2, below operation 10 can perform on string 1, find the minimum number of edit required to convert string 1 into string B. Got it? So either I can do insert or remove or replace. Oh, what we did, replace, add, remove. So all of the above operation, the cost of 1, both the strings are all uppercases. So we simplify the problem. Then we can solve it together and solve it in algorithmic way. Okay. So let's try to solve this. String 1 is cat, string 2 is cut. What's the edit distance of these two? Is, do you see? By replacing A to U with the cost 1, I can make string 1 to string 2. Clear? So we can convert string 1 to 2 by modifying A to U. So if I touch A to U, then I can make cut from cat. Okay, so edit distance is approach given two strings of length m and n. If the last characters of the two strings match, we do not change anything and recur for length of m-1 and m-1, which we saw in the LCS. And else we compute the minimum cost of the 3 operations, either insert, deletion, or modify, and take the minimum of these 3. Okay, now LCS is a little extended. So in code-wise, if it is match, I'm going to diagonal value, then keep running edit distance. Either I can find 3. I can run insert, remove, or replace by reducing n ones, reducing m ones, or go to the diagonal by replacing it. Okay? Clear? Okay. So we can practice with the Sunday and Saturday. Okay, if you want to. Then let's solve this. Let's see the problem. So this is overlapping substructure problem. Let's say you have a length of 3 and 3. If it is match, okay, I found the solution. If it doesn't match, I can replace 1, I can add 1, I can remove 1. Okay, then from here I can do replace by adding, remove. Okay. So edit distance 2 of 2 is edit distance 2 of 2. This will match. Then therefore I don't need to compute again. Clear? Then we can keep repeating these procedures and to find the answers. All right. So minimum edit distance as a search. So every day we are using edit distance when we type something and your Google search recommends something. So by having edit distance 3 and 4, the Google can find the dictionary word or the commonly searched word. Okay. The space of all the space of the all edited sequence is huge. We cannot recommend everything, right? And we cannot afford to natively navigate naively. Lots of distinct paths wind up at the same state. So we don't have to keep track of all of them. So just find the shortest path to each of those revisited state, meaning we can use dynamic programming. Okay, let's solve the problem. So given two strings of cart and march, find the edit distance to convert cart into march. We human can do quickly with 3 times. How? I want to make cart to march. What's the best way to? So convert to C to M, A, R, converting T to C, then adding H. Then with the cost of 1, 2, 3. So edit distance of length, edit distance of the string 1 and 2 is 3. I can quantify. Okay. So let's solve this. Edit distance, let's say it is from and to. So from null, how can I make null? Which is 0, null and null, right? Null to M, I'm adding M, which is +1. Null to A, null to MA, therefore 2. Null to MAR, 3. Null to MARC is 4 and 5. Okay. Then C to null, I have to delete once, right? C to M, I have to replace it. Okay. C to A, C to MA, oh, I should do 2 actions. Either I replace it with the C and M, C to M, then add A, or any other mechanism. I can add M first and replace A to C. Then it should be 2. R doesn't match, so C to MAR is 3 value. C to C, oh, matching value, then it should be same value of the previous, right? Because it is match. If not, what should I do? I'm choosing the minimum value +1. Okay, let me go over again. So by using dynamic programming, meaning I'm using the previous computed result. Okay, the diagonal is replace. This value is adding. This value is a delete. Okay, so there's nothing. 0 to M, I can add 1. So 0 to A, oh, I can add M, 4, and 5. Okay, so from here, C to A is I can do deletion. Then it is cost of 1. Now from here, I can run because, so M and C doesn't match. What can I do? I'm using the biggest value, the max value of the previous one. Oh. I can add not the max value. I can do 3 operations. I can do replace, I can add, or I can delete. Among those, I choose the minimum value +1. Why is the minimum value? If it is not match, I can take 3 actions. Among 3 actions, I'm choosing the minimum cost, right? Edit distance of finding the minimum move, then I can make, then I can convert it from string 1 to string 2. So C and A doesn't match. Out of 3 candidates, I'm choosing the minimum and +1. C and R doesn't match. Out of 3 matches, I'm choosing the minimum and +1. C and C, oh, I match. What do I do? I'm just choosing the minimum value that I can change, that I can choose. C and A doesn't match. So what do I do? I'm choosing out of 3 candidates and +1. Okay, so A, A, there's no value and no value. So choosing the minimum value +1. So M and A doesn't match. So choosing the minimum value out of 3 +1. So A and A, oh, it is match. Then out of 3, then I'm choosing the minimum. Okay, A and R doesn't match, so I can choose out of 3 plus 1. C and A doesn't match, so choosing minimum plus 1. A and H choosing minimum plus 1. Okay, R and 0, no value existing, so choosing the minimum plus 1. M and R and M doesn't match, choosing the minimum plus 1. A and R doesn't match, choosing the minimum plus 1. Oh, R and R match, so I'm using the previous one. Out of 3 candidates, I'm choosing the minimum one. C and R doesn't match, so choosing the out of 3 plus 1. H and R choosing the minimum plus 1. Okay, so only one candidate. So out of 3 candidates, choosing the minimum plus 1. M and P doesn't match. M and R doesn't match. C and T doesn't match. H and T doesn't match. Okay, so the result is the final value of this guy. Okay, so this is result. What human can do, I can replace A to C to M, A or replace it and adding. So if you see how this is 3 was choose either of these two, how this was choose, how this was choose, how this was choose, how this was choose. So if I go back to the point, it choose to replace, it choose the adding H or replacing it, adding H, then replace it, C to C and T, then replace it, and replace it. So if you find the path from here, then you can see how they are converted. So from C to M, you replace it. Then A to A is match, R to R is match, C to T is replaced, T to H is added. Okay. All right, so this is the code. If it is match, I'm choosing the diagonal value. Match with, so if it is match, I'm choosing the diagonal value. Sorry for the misunderstanding. So if it is match, I'm choosing the diagonal value. If not, I'm choosing out of 3 candidates, and among those, I choose the minimum, then plus 1. So if it is match, I'm choosing diagonal value. If not, then I will do either of 3 and choose the minimum cost of it plus 1. All right, so this is called edit distance. Clear enough? Okay, so edit distance with the weight. Why we need to weight the edit distance? Why would it add the weight to the computation? The spell correction. So some letters are more likely mistyped than others. Biology. Certain kinds of deletion or insertion more common and more likely than the others. Why? Why is this happening? Let's think about the spell correction. So this is a confusion matrix for the spell error. So if you look at some numbers, okay, M and N is more confused than the others, and O and E is confused. A and E is commonly confused. This number, U and E is commonly confused. So if it is this diagonal value, it is match. So 180, M is confused with the N. 146 is I is confused with E, A is confused with E, and O is confused with the E. Why is this happening? Because we are using the keyboard. So I typed E and R, E and F were commonly wrong. Okay, if you look at the D, from the D, E is confused. R, S, T, E, R, S, sometimes T, and F is confused because my fingers are make mistake because I'm using human body. Okay, then let's go back to the point where we started. Then we can do much smarter recommendation by typing it. Based on the edit distance, I can recommend more cleaner text, auto spelling, right? You type something, but it's wrong. You can recommend a better letters, okay? So in English, it is widely explored and there are many research on it, but in Korean, it is too diverse. And also we don't write the Korean light is somehow different to the English grammar. At the the writing sequence and writing pattern is different. We use the how it is pronounced. Okay, so because we have some distance from English, so our research on the Korean language is not that common. So if you can do, you can take up the market of Korean. Also, the market size of the Korean is so small, they don't invest a huge money on it. Okay, any question about the edit distance?
Professor?
Yep.
I have a question about the spelling correction matrix that you just showed us.
Mm.
I saw there were like numerous numbers on the alphabets. Do you have any idea how those numbers were calculated or came up?
This one?
Yes.
Confusion matrix?
Yes.
Okay, so confusion matrix. So let's say y, this value is correct. Y is a substitution of the x and y is correct. So you try to type y, but you actually typed these different letters. Okay, so your job is typing some letters, but you actually typed in wrong. Okay, meaning, so we do the user study. User study meaning in the closed lab, I'm giving you some text, and can you type it on the keyboard? Then people try to type it. Because the human finger make a mistake. Whenever I made a mistake, then that increment, that counter is incremented. That counter is incremented. Then we can see why is this numbers are, why is the typing is mistyped. Okay, because it is completely matched to the keyboard layout. So the typing pattern of it. That's how we quantized this matrix.
Okay. Thank you.
All right. Any question? No. Then go back to the slide in here. So this is the capture of 2018 Google I/O. So Sundar Pichai, the CEO of the Google, and I want to show you this.
I think you need to share the audio too.
How can I share the audio? Mute. Share the computer sound. Okay. Can you hear?
Yep. Thank you.
How can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Mm-hmm. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like. What service is she looking for? Just a woman's haircut for now. Okay, we have a 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
Okay, that is a human, that's not human conversation, but AI conversation. The key word is, how can you make close to human? Then you have to have a huge dictionary. What makes your language, your spoken language more natural to the others, than the others? Okay, that is all the basic of it. There is edit distance, and how can you make more natural? I want to share more conversation.
See how may I hear you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people? When? Today?
Next Wednesday at 6 p.m.
Oh, actually, we reserve for like after like 5 people. For 4 people, you can come.
How long is the wait usually to be seated?
For when, tomorrow or weekday or?
For next Wednesday, the 7th.
Oh no, it's not too busy. You can come for 4 people. Okay.
Oh, I gotcha. Thanks.
Bye bye.
Okay, even the human correspondent is not English speaking. I can say that, right? Native, she's not native. Even they are not speak fluently, then AI can handle this. Meaning, our listening is more easy to listen than the standardized English. Even someone speaking Chinese or someone speaking in some different tone, it is very hard to understand for the first time. But AIs always give you the standardized, then everybody can easily understand. Okay. One more video.
But it gets tricky during holidays, and businesses get a lot of calls. So we as Google can make just that one phone call and then update the information for millions of users, and it'll save a small business countless number of calls. So we're going to get moments like this right and make the experience better for users. This is going to be rolling out as an experiment in the coming weeks, and so stay tuned.
Okay, this is how the Google's the design in Google's NLP make the AI more improved. It's working. All right, it's the backbone of it, the CSC373, the AI and algorithm. Okay, all right. Thanks for coming today, and thanks for your attending. All right, any question? No. Okay. Okay. Any question about today's class? Nope. All right. Let's call it a day. Thank you.